Assalamu alaikum. So let's start with lecture number 10, which is the frequency response of zero order hold. Now, if you remember, the transfer function for the zero order hold was equal to 1 minus exponential minus t s over s. Now we need to find the frequency response, so this means that I need to substitute instead of s, j omega. So if I'm doing so, I will get the transfer function in the frequency domain for the zero order hold can be written as 1 minus exponential minus j t omega over j omega. Now, simply, this can be written as, if I'm taking a factor, exponential of minus j t omega over 2, then here I must multiply by exponential of j t omega by 2. So you know that if I'm multiplying, this will equal to 1 minus exponential of minus j t omega over 2 over j omega. Now, if we recall, sine theta can be written in terms of the exponential as exponential of j theta minus exponential of minus j theta over 2j. So simply now I can say let theta equal t omega over 2. Then this means that I can write the zero order hold transfer function in a frequency domain as exponential of minus j theta exponential of j theta minus exponential of minus j theta over j omega. Now here I'll multiply here by 2. So here I should multiply by 2. So now this one will be the sine theta. So simply now the zero order hold transfer function in frequency domain now can be written as 2 exponential of minus j theta sine theta over omega. Now here I can multiply here by t, so here I can multiply by t. Now this one too, I can rearrange it to be t exponential of minus j theta sine theta over omega t over 2. So now let's substitute instead of theta t omega over 2. So now the zero order hold, the frequency response will be t sine omega t over 2 over omega t over 2 exponential of minus j t omega over 2. Now, as any complex number, this one has amplitude and angle. So now the amplitude will equal to t, the amplitude of the sine omega t over 2 over omega t over 2. Now, the angle of the zero order hold will equal to, now here I'm having two terms. The first one will be the angle is the sine, the angle of the sine of omega t over 2. The second one is the angle of the exponential, so here I'm having minus t omega over 2. So now at omega equal 2 pi over t at the sampling, the sine of omega t over 2 will equal sine of pi, which will equal to 0. So this means that the amplitude of the zero order hold will equal to 0 at the sampling frequency, or multiple of the sample frequency will equal to 0 at omega s or multiple of omega s. Now, the angle at omega equal 2 pi over t, then the angle of the zero order hold will equal to minus pi at omega s or multiple of omega s. So if I need to plot the frequency response for the zero order hold, the amplitude as function of omega, so the amplitude versus the frequency at omega equal to 0, the value using the L'Hopital rule will equal to t, and this one will equal to 0 at omega s, 2 omega s, and 3 omega s, and so on. And it will be attenuate. So for example, at omega s over 2, the value will be 0.637 t. The value at 3 omega s over 2 will be, if I'm substituting the amplitude 0.212 t, and the value here will equal 0.127 t. Now, if we need to plot the angle of the zero order hold, as we state before, the value of the angle will be minus pi at omega s and multiple of omega s. Let's assume this is 3 omega s, and let's assume that this is the line of the minus pi. So the angle will start increasing in negative from 0 until reaching the pi, the minus pi. It will repeat itself. So this is the frequency response of the zero order hold. As we can see, the zero order hold does not perfectly approximate the low pass filter. In order to get better approximation for the low pass filter, higher order holds is needed. But simply this will add more complexity and will add a delay since it will reduce the stability. But this will complicate the system and add delay, which will reduce the stability margin. So that's why usually we are using the zero order hold. So that's why the zero order hold is used widely in digital control. Simple and add less delay to the system. So now let's discuss the obtaining of the Z transform of the function involving the terms 1 minus exponential minus Ts over S. So obtaining Z transform of a function involving the term 1 minus exponential minus ts over s, which is a common factor in the zero order hold and the first order hold. So if we recall, if this is the input, let's call it R of s, and here we have the zero order hold, the transfer function for the zero order hold. And here let's assume we have a plant, which is G of S, and the output, let's assume it is denoted as Y of S. So this can be simplified as one block, and let's assume this block is called X of S, which relate the input R to the output Y. Now, X of S here will equal the transfer function for the zero order hold, which 1 minus exponential minus t s over s multiplied by g of s. Now we need to find x of z, which will be the z transform for x of s. Now we know that there is a relation between the s plane and the z plane, and they are related by z is equal exponential of t s. So simply, this means that this term is z. So this means that x of z can be written as 1 minus z minus 1. Now we need to find the z transform for the remaining part, which is g of s over s. Now in terms of z, this can be written as z minus 1 over z, the z transform for the g s over s. The same thing we can do if we have a first order hold. So again, let's assume this is the R. Let's assume here we have a first order hold circuit. And here we have a plant, which can be represented by G of S. And this is the output, Y. Now this one, we can simplify it as a single block. This is the R, those two blocks in series. So this will be the X of S, and here we have Y. Now, X of S will be the transfer function for the first order hold, which is 1 minus exponential minus T S over S all squared Ts plus 1 over T, and we have the G of S here. Now we need to find X of Z. So X of Z will equal. Now again, this one is the Z, so it will be 1 minus Z minus 1 squared, the Z transform for the remaining part, which is the T S plus 1 over T G of S G of S over S. Also, it's very important to evaluate the star signal in S domain. So let's discuss the evaluation of E star of S. Now, we know that in general, if we have a continuous signal E of t and we have a sampler, then we will have E star of t, and simply we can calculate E star of S to be the Laplace transform for E star of T, which will equal to the Laplace transform for summation from k equal to 0 up to infinity E of k delta of t minus k t. This is the direct calculation of the starred function in terms of Laplace. And if we have E star of S, we can calculate E of Z. We know that E star of S is equal E of Z such that Z is equal exponential of Ts. So let's fix it. So E star of Z is equal E of Z such that Z is equal exponential of Ts. So again, if we have E of Z, we can also calculate E of S. So also, what about if we have E of S? If we have E of S, can we find E star of S? The simple answer is yes, using the residual method. So simply here we can state that E star of S will equal the summation of the residue of E lambda. Here I'm changing the variable, complex variable from S to lambda. 1 over 1 minus exponential of minus t s minus lambda at poles of E of lambda. And you know that the residue, if we have simple root, it will evaluate it as, let's assume that E of lambda has simple whole at lambda equal lambda 1. So in this case, the residue will be R1 at lambda 1, which will equal lambda minus lambda 1 multiplied by E of lambda over 1 minus exponential of minus t s minus lambda evaluated at lambda equal to lambda 1. Now, if lambda has a repeated root, E of lambda, if E of lambda has a repeated root of order m at, let's say, lambda equal lambda 2, then here R2 evaluated at lambda 2 will equal 1 over m minus 1 factorial d m minus 1 by d of lambda m minus 1. Then we multiply lambda minus lambda 2 to the order m by the E of lambda over 1 minus exponential minus t of s minus lambda, and this one will be evaluated at lambda equal to lambda 2. So let's take example for evaluating the E star from E of s. So let E of s is equal 1 over s plus 1, s plus 2. So the first thing, I will change the complex variable from s to lambda. Lambda is the dummy variable. So here we have E of lambda will equal 1 over lambda plus 1, lambda plus 2. Now, the roles of E of lambda, we have simple poles at lambda equal to minus 1 and lambda equal to minus 2. So now E star of s will equal the residual R1 at lambda equal to minus 1 plus the second residue at lambda equal to minus 2. Now this will equal the first thing, if I multiply by lambda plus 1, this will be cancelled and I will end up with 1 over lambda plus 2, 1 minus exponential of minus t s minus lambda evaluated at lambda equal minus 1 plus the second one will be, if I multiply by this one, lambda plus 2 to be cancelled, and I will end up with 1 over lambda plus 1 multiplied by 1 minus exponential minus ts minus lambda evaluated at lambda minus 2. So it will be 1 over lambda plus 1, 1 minus exponential minus t s minus lambda evaluated at lambda equal to minus 2. Now if I evaluate E star of s will equal 1 over 1 minus exponential minus t s plus 1 minus 1 over 1 minus exponential minus t s plus 2. Now we know there's a relation between the E star of s and the E of z. They are related by z is equal exponential of t s. So this is very interesting because we can now calculate E of z relying on the formula of calculating E star of s. How we can do that? Now let's see. Now we know that E star of s so now we need to find a method to calculate E of z. From the same formula we calculated E star of s. If we recall, E star of s was equal to the summation of the residue at poles of E lambda, the residue of E of lambda over 1 minus exponential minus t of s minus lambda. Now, if we put z equal exponential of t s, now this one will become e of z will equal to the summation of poles so E of z will equal the summation of the residue at poles of E of lambda residue of E of lambda over 1 minus exponential of t lambda. Now, if you notice, this one here can be written as exponential of minus t s exponential of t lambda, and this one will be z minus 1. So z minus 1. So now, if we change the complex variable from lambda to s, because now we need to calculate E of z. So this means that now E of z will equal to the summation of the residue of E of s z over z minus exponential of t lambda at poles of E of s. So this one will be s, sorry, because we are changing the variable, the dummy variable from lambda to s. So let's take an example to calculate the x of z given E of s. So let's assume that we have x of s, which will equal 1 over s square s plus 1. Now the poles here is s equal to 0, repeated twice, which means that m here is equal to 2, and we have s equal to minus 1, simple root. So here we need to calculate the residue for repeated root and for a simple root. So now x of z will equal the first residue calculated at s equal to 0, which is the repeated, plus the second residue calculated at s equal to minus 1. Now the first one is the repeated, the degree of the to order m, so r1 will equal to 1 over 2 minus 1 victorial. d 2 minus 1 is 1 by ds. Then I will multiply the root, which is the s square, by the function itself, which is 1 over s square s plus 1 z over z minus exponential of t s, and I will evaluate at s equal to 0. Now plus the second residue, which is the simple one, which will be, I will multiply by the root s plus 1 by the function itself, 1 over s square s plus 1 z over z minus exponential t s. Then I will evaluate at the root, which is s equal to minus 1. Now this one will cancel this one, and this one will cancel this one. If we differentiate, we will get that x of z will equal to minus z multiplied by z minus exponential of t s plus z plus 1 multiplied by minus t exponential of t s over the s plus 1 squared z minus exponential of t s squared, and I should evaluate at s equal to 0. This is the R1. And the second one is 1 over s square z over z minus exponential of t s. I should evaluate at s equal to minus 1. Now, if I do the evaluation, I will get z minus 1 minus t over z minus 1 squared plus this one. If I evaluate at minus 1, it would be z over z minus exponential of minus t. So this is how to calculate x of z. We know that, if we recall, that x of z can be calculated from the z transform for x of k, which actually equal the summation from k equal to 0 up to infinity x of k z to the power minus k. Or simply, now using the residue, we have a direct method to calculate x of z given e of s. This will be added to the methods of calculating x of z. Now, lastly, we need to discuss or list some property for the star function in terms of Laplace. So let's discuss the properties of E star of S. The first one here, that E star of S is periodic in S with a period of omega s. So if E of S has pole at certain location, let's say S equal to S1, so this implies that E star of S must have poles at S equal S1 plus J M omega S, due to the periodic nature of E star of S, where M is integer equal to 0, plus minus 1, plus minus 2, and so on. So this means that what about the zeros? the, the zeros of E of S do not uniquely determine the zero's location for each style of S. So the poles of E of S decide the poles of E star of S, but the zeros of E of S do not uniquely determine the zeros for E star of S. What about the relation between the poles and in the S plane and the Z plane? We know there's a relation in between. So finally here we can write the poles of E of S determine the poles of E of Z. So if E of S has a pole at S equal to S1, then this implies that E of Z will has a pole at Z1 which equal exponential of T S1. And this is the end of chapter 3.